So welcome back to our video on rotational dynamics. We're talking about objects rolling down ramps. And what we've done so far is we've calculated the moment of inertia for an unusual object, Abraham's exercise wheel. And I'm going to pick up the process of going through and solving the problem for the acceleration of Abraham's exercise wheel or any other object as it rolls down the ramp. We'll also take a look at finding the velocity of the object, and we'll also go back through and look at the LoggerPro video data I collected and see how well it matches our predictions. So first I'll use conservation of energy to predict the final velocity, and we can use motion equation 8 to find the acceleration of it as well. That's assuming that this is moving at a constant rate of acceleration, which it is. There's constant forces acting on it. Secondly, we'll use a different method using a free body diagram and Newton's second law, but we're going to use torques rather than forces to do this. And you're going to find that this is much faster to do for this type of problem than using energy and equation 8. This is a one-step process really versus a two-step process, which takes a... So let's try finding the acceleration down the ramp using energy techniques. I'm going to do this as a general solution using a non-homogeneous object because the object I'm dealing with is non-homogeneous. You should do this using a homogeneous object. I would do it as a general solution, so you can use this for other purposes perhaps, using I equals kmr squared where k is for a hoop or a solid ball, whatever. So some relationships that we're going to use along the way is conservation of energy. And so to set up a conservation of energy problem, we need a before and after scenario. So here we are at time 0 or position 0. And we'll look at the energy there, which consists of some height energy, some gravitational potential energy. And the object has not started rolling yet, so its kinetic energy, both translational and rotational, is 0 to start. Along the way, we can actually convert our rotational speed into a translational speed quite easily using v equals r omega. When we reach the bottom, our height drops to 0. But what we do have is a rotational energy built up at this point, both rotational and translational kinetic energy. So we'll be using two components in our formula for that. So using conservation of energy, so we can take the total energy at point 0 and compare it to total energy at point 1. We're going to assume that there is no non-conservative forces at work here, for example friction, air resistance, or somebody pushing or pulling it. And what we end up with is, we said before, we've got height energy to start with, and we've got speed energy down here in two forms. A translational component from our translational velocity vx1 and our rotational quantity. And substituting our formulas for those two pieces in, we get this, and then we can start making some substitutions. And we can do some substitutions into the formula. We're going to substitute for this height, it's L sine theta, whatever the length we're traveling down the ramp. And for the omega, we can once again use omega equals Vx over r and substitute in here. And we're also going to use, because since we see this Vx1 squared popping up all over the case, and we really want to find acceleration, we could use this formula directly to solve for Vx1, which you should do. You're going to need to find Vx1. But I'm actually going to go through and substitute it out and go directly to my acceleration. And to do that, I'm going to use my constant acceleration equation number 8, which has the Vx final squared in it that we're going to substitute in over here. And we'll see how this works out for us. Our initial velocity, of course, is 0. And so our delta x is actually the length of the ramp here, L. And what we're going to do is we're going to solve this for Vx1 squared, done. And then we can substitute out for Vx1 squared over here to AXL. And I'll do that in two spots. So now that we've substituted, what we can do is we can do some simplification here, and remember what we're trying to solve for is AX. And so the first thing we can do is we can cancel out the halves and the 2's that are multiplying by each other. And you'll also notice that we have the length of the ramp showing up in all three of the terms, and so we can cancel that out. So the length of the ramp doesn't affect the acceleration. because acceleration is constant. So we've got this resulting, and what I've done here is I've actually factored out our acceleration using common term factoring. So if we divide by this factor, we can solve for ax. And one thing to notice right off the bat when we do this is if we have an object that has no rotational mass, our moment of inertia, that zeroes out, then our masses will cancel and we'll end up with g sine of theta, which is just a sliding object. Alright, so that's good news. Now we can also simplify this a bit more, and what we'll do is we'll clear this improper fraction by multiplying the top and the bottom of this fraction by r squared and see what happens. And what we get is this result right here. This looks like another moment of inertia here, mr squared. In fact, you might recognize this bottom here as really it's an application of the parallel axis theorem. And what we're doing here, rather than looking at the object at its center of mass, this formula is sort of encouraging us to look at the object as it rolls down at the bottom at this point right over here. And so really this is taking a look at the bottom here. It's dividing by the moment of inertia around the edge. And that's a good hint as to how we should solve these problems using forces as well. Maybe we'll want to look at rolling this around the edge rather than around the center of mass as we look at the forces. So I'd like to step back for a moment and just to take a look at the final velocity of these objects as they roll down the ramp. And let's compare them to things that we've done before, sliding objects, or for that matter, falling objects as they move down the ramp or come down to the ground, regardless of the path. We've done this using a couple different methods. Before, what we've done is used Newton's second law, and we've used a rotated axis to work out the acceleration for a constantly accelerating object. And we've also used energy to look at the energy just going from point 0 to point 1 for a sliding object. And when we looked at energy, we found that the path really didn't matter. I don't care if I was going downstairs, going down a ramp, or going straight to the ground. The velocity at the bottom was the same as long as there was no non-conservative forces at work. So let's go ahead and solve this rotational problem for our final velocity and see what happens. What I'm going to do next is I'm going to pull out our vx1 squared, and then I can just take the square root of both sides. So here's our resulting relationship. And remember, I'm doing this for a non-homogeneous object. For a homogeneous object, you should have, before this, probably at one of these points up here, substituted in I equals k mr squared for your relationship and done some cancellations earlier on. But for a non-homogeneous, I was stuck with it the whole way because I didn't have a simple radius or a simple mass or anything. And I come up with this result. But we can take a look at this now and compare. Once again, if we have a sliding object, we have no rotation, so our I goes to 0. And we come up with the square root of 2gh, as before. So it turns out that whether we're rotating or sliding, the same result can be used. Of course, I would not try to do this calculation for a sliding object using rotational energy because it takes too much time. I would use simple conservation of energy without all this other junk in here. But I just wanted to show you that the two results end up being the same value if I goes to 0. And you'll notice the only other thing I did is I just rearranged and got rid of my complex fraction here. And once again, you can see down here, this is my moment of inertia around the edge of the object using the parallel axis theorem. So remembering our back to the races, we found that for homogeneous objects, the type of the object was what controlled the rate down the ramp. As long as the objects were the same type, they rolled down the ramp at the same rate, and the mass and the radius had no bearing whatsoever on how quickly they went down the ramp. And it was really the distribution of the mass that affected the rolling rate. And here's our result, and our result has mass and radius all over the place, so it doesn't look like our conclusion up top is true, unless of course something cancels in here. And once again, if you have a homogeneous object, you'll see that things do cancel. Let's just take a look for a homogeneous object and see what happens if we use k mr squared rather than our non-homogeneous setup. And once again, remember, the k here would vary depending on what type of object you use, how that mass is distributed. If the mass is all the way at the edge, we have a 1 out here. It's a definition of what inertia. And we have for a cylinder, it was a half. For a sphere, it was 2/5, etc. So if we start out with our two equations from the last page, the question is, what happens if we substitute out into these things? And so first thing I'm going to do is substitute kmr squared in for the moment of inertia about the center of mass. So first of all, does mass matter? Well, look at this. We've got mass canceling out in three places here. We've got mass canceling out in all three places here. So it turns out mass, quote unquote, doesn't matter. Of course, in real life, mass does matter, but as in terms of the acceleration, it does not. Now, what about the radius? Once again, in each one of these systems, I've got radius, radius, and radius. They all cancel. And so we can show once again that radius really doesn't have an effect theoretically. And what we end up with is a set of equations for a homogeneous object that just relates to this value of k. So what do these mean? Well, a rotating object, rather than accelerating at g sine theta if k equals 0, if k is some value that's non-zero, for example 1/2 for a cylinder, a solid cylinder, or 1 for a ring in the worst case, we would actually, if it was 1 in the worst case, we would get 1 plus 1 on the bottom, and our acceleration would be cut in half. And so depending on this value of k, how the mass is distributed, this value could be as high as 1 for k, and that will slow down our acceleration by as much as a half. And if the object only slides, well, k is 0, and we get our other simple relationships from before, square root of 2gh and g sine of theta. Alright, so we've seen how to use energy to calculate the acceleration of an object going down a ramp. Now let's go ahead and use force to do that. And I've drawn this object to be very large so that you can declutter your work when you actually do this. It's best to use a very large circle to show your forces, otherwise things get compressed into a very small space. I'm going to do this as a general solution, so I don't really want the specific data right now. I'll substitute that in later. And so remember, we're doing a non-homogeneous object, whereas you're going to do a homogeneous object, so you want to substitute in kmr squared for your moment of inertia. So we're going to start with the second law. And our second law for torques is the sum of the torques equals the moment of inertia times the acceleration. It's the rotational equivalent of the sum of the forces equals mass times acceleration. So our acceleration is down the ramp, and we're going to draw on our forces to start with. We've got our force due to gravity. We've got a normal force pushing up from the ramp onto the object, and we've got a frictional force. Now this frictional force, the question is, which way do you draw a frictional force for an object to allow it to roll down a ramp? If you have no friction on a ramp, this object will never roll. It will slide the whole way. So you need that friction in order for the object to roll without slipping. And that's an important thing to look at up front. Is the object rolling without slipping or not? If it's rolling without slipping, you need some friction in order to cause that to happen. Using that idea, you can actually think of which way that force will actually be directed. If this object does slide down the ramp and friction eventually is going to stop it, the friction is going to have to oppose that sliding motion, so the friction has to be pointed up the ramp. So we're going to start out by assuming that we're going to use the center of mass as the rotational axis and see what happens here. So here's our center of mass, and that's where we could actually draw on, if we would like to, our angular acceleration and our omega, etc. Keeping in mind as well what the direction of this is, if you use the right hand rule, you would find out that this rotation is pointing into the screen. So if we look at this, we see that our gravitational force and our normal force pass through the rotational axis, and so they are directly at the axis, and there is no moment arm through there. There's no radius separating them from the axis, and so those will cause no rotation. And if you need a refresher on this, you should go back and look at the video where I summarize how torques work on objects. The frictional force, on the other hand, it is working through a radius of r, and you can actually see we've got a nice 90-degree angle as well. And so if we were to calculate the r cross f to find the torque, our angle is 90 degrees, so our sine of 90 degrees would be 1, so we just get r times f as our result. And if you were to use the right hand rule to look at the direction of this torque, you would see the direction of this torque, if you use the right hand rule, r crossing into the f. If you curl your fingers from the r over to the f, the only one way to do it is your thumb moving into the screen. It will give you a clockwise rotation of this circle, and it's matching up with the direction of motion I had put up here already. Now, the only problem with this is that I could use this to calculate something, but it's not going to help me get the acceleration of the object because, first of all, I don't know what our static coefficient of friction is, and without that, I'm sort of stuck. So let's try a different method here, and I'm going to actually change our center of rotation from the center of mass. Here's our new rotational axis that we're going to try out. And remember, when I looked at before the calculation we did with energy, it looked like it was leading us to this conclusion in any case. So using the edge of the wheel as our center of rotation, we find that two of the objects once again have a moment arm of 0. We're trying to tug on the rotational axis, and that's not going to cause a torque. And our normal force is actually aligned with the rotational axis as well, so that's not going to cause a torque. We can't cause something to rotate if we're pulling on the axis itself. So the only one that's going to actually cause a torque and this thing to roll is the force due to gravity. And that's good because what we need is we know everything about the force due to gravity, and we can plug it in here as a single torque and then calculate the alpha. We already know I, remember, we calculated that using our numerical method, and we have a value for that rotational inertia, both around the center of mass and around the edge. So this is what we're going to do. And so here's our moment arm, R, and remember, we're going to find this torque, so we have to do R cross F, and the angle in between that we'll need is this theta right here. And if you do your geometry, you'll know that this angle here is going to match that angle there. So we're going to take this R cross with the F, so it's going to be RF times sine of this angle. So once again, for our rotational axis, we're taking clockwise is positive in this case. I'll just arbitrarily choose positive to be clockwise. The typical method is they use clockwise as negative, but we can choose positive whatever way we'd like. The torque, once again, if you do your vector cross product and use your right hand rule, if you curl your finger through this radius into the force due to gravity, there's only one way you can do it. Your thumb has to be pointing into the center of the page, and that matches the rotational axis direction as well, using the right hand rule. So we're going to choose clockwise into the page, which is our negative k direction, but we're going to call it positive. Recall that we're using the moment of inertia around the edge, which is our center of mass plus md squared. And we already have a number worked out for that, and we'll just plug that in later. And so these are the three possible torques that we'd have, but of course two of these torques are 0 because one of them is parallel to our motion and both of them are aligned directly with our axis and pulling on the axis, which isn't going to cause any rotation. The only one that causes rotation is our torque due to gravity. And once again, we're going to use torque equals RF sine of theta, with our theta being given up above. And we can also make a substitution in for our alpha. So I'm replacing our torque due to gravity with this cross product, R times the force times sine of theta, R mg sine theta. And I replaced our angular acceleration with ax over r, using the relationship between rotational and linear variables. And when we solve for ax, well, what do you know? We got the same result we had on the prior page using energy methods. So that's good news. The answer should be the same. You'll notice that this took a lot less work than the energy method. The energy method in many cases is faster, but in this case it turns out to be a little bit slower. And we had to find the acceleration going through one of the motion equations as well using energy, so it added a little more time. So this turns out to be a very fast, efficient way to find the answer. And if we just go back to our results now, we found out that our acceleration is the same for both cases. Our velocity works out to be the same as well. And we can go ahead and plug in some numbers and find out our theoretical velocity. And this is for Abraham's wheel using non-homogeneous problem that we had here. I'm plugging in our results, and we have a predicted value of 2.35 meters per second for the final velocity. And for the acceleration, if we plug in our numbers, we found a theoretical acceleration of 2.36 meters per second squared. These happen to come very close to each other because it turns out the time in both these cases turns out to be exactly 1 second, as it turns out. So this is just a fluke that these two numbers ended up being so close to each other. So here's our LoggerPro results, and you can see I had a little bit of help doing this work from some famous students. I was saying that the time just happened to end up at nearly exactly 1 second, which is why some of our numbers matched up so nicely. But you'll notice that I use a quadratic regression because I'm assuming we have constant acceleration, which I think is a good assumption. We have constant forces acting on the object. That should cause constant acceleration down the ramp. This is the length of the ramp I picked up experimentally just to see what length I was dealing with, and you can do the same for your object after you do your motion analysis. The other thing you can pick up off of this is you can take a look to see what your experimental final velocity is. Just be careful. I put an asterisk next to this because this is not a direct measurement that's done by the system. It's actually a calculation. They're using some sort of methodology, Euler's method, or some basic calculus to come up with an estimate of what these velocity figures are. The number we're looking for the acceleration is right up here. We're assuming it's a quadratic fit, so we've got the formula for a parabola here, ax squared plus bx plus c, where if we match that to our motion equations, that a is 1/2 of our acceleration. So our acceleration should be double that coefficient a. And of course, this is what you're going to write up in your conclusions. And what I would have here is 2 times 1.082, so I end up with 2.164 meters per second square for our experimental acceleration. Another look at the acceleration is down on our velocity versus time graph, but I put an asterisk next to this again because remember, this is indirect data here because it's been going through a series of calculations that they've done using Euler's method or some basic calculus to figure out what the velocity is from the position data. So I'm going to go back and use this as the more reliable data, but you can see the numbers are fairly close. So let's summarize the results and calculate some percent errors. What I find out is that both our velocity and our acceleration is about 8 or 9% below what we'd expect. And the question is, these aren't bad numbers, this is fairly close. The question is, can we explain why these are negative errors and why they're somewhat large, but not crazy out of the ballpark numbers? What would cause that? Well, we can always, blame those kids in the picture. They weren't measuring things correctly. Not that I've ever seen students do that before. And then there was me placing VA points on the LoggerPro, setting my scale, etc. How accurate was I doing that? It was a fairly small spread of points, especially in the beginning, and so those numbers could be off a little bit. Both of these errors, though, they can run either way. I'm not sure if these would increase my error or decrease it, make it positive or negative. The big error, though, and the big question is, can we figure out a source of negative error because this is such a large negative error, 8 or 9%? And there is a case, and we know this, with video data, we have a big problem, especially if our camera is very close to our subject, with perspective error. And just to refresh your memory on that, I think the camera in this case was probably only about 1.5 meters away from our plane of motion. This is our ramp. So the objects start here, roll down the ramp, and we're videotaping the data. The big problem here is that if we look at, for example, objects moving in a distance versus objects moving close to us, if I have a car that moves at 50 miles per hour 10 feet away from me, right in front of me, it's going to zoom by really, really quickly. But if you look at a car a mile away moving 50 miles per hour, you can see an ant crawling faster than that. And so the distance an object is from the perspective of the viewer is going to affect how fast it appears it's moving. And what's happening here is at the extremes, we have a longer distance, as shown in the red lines, than we do for the object when it's in the middle of the picture. And so out of either end, we're going to see the object appearing to be moving slower than it is. And that's going to cause our acceleration numbers to be lower than they should be. And that gives us our negative error. In this case, just to show you, at the ends, at both of these ends, if you use Pythagorean theorem to calculate what the distance is, this distance is actually 7.5% further away than it is in the middle. You could do some more calculations and calculate what effect that is. But remember, this really turns into a calculus problem, because as we get closer to the middle, we get truer and truer data, and then we go past the middle, we get further and further away again, and it has an apparent effect of slowing it down. And so to get the true effect overall, you'd have to set up a calculus problem to work out the entire issue here, and you could potentially calculate a real percent error and make a correction to your data for this as well. But you can see that would be a good explanation of why we have a negative error persist through our data, and I think you'll find the same when you do your data. Just to show you what would happen if we move back to baseline. If we move the baseline back even just a half a meter to 2 meters, you can see the apparent distance is reduced by quite a bit. And if we were even to go back further, if we had the right type of equipment, and really we'd need a telephoto or an optical zoom to do this, and our nice cameras that we have, our cell phones, don't have good zooms typically when you're doing video, or if they do allow you to do it at all. But if we were able to do something like that, you'll notice if we moved back 5 meters with an optical zoom, which wouldn't be hard to do with a decent SLR camera that could do high-speed video, you reduce that distance error down to less than 1%, which should practically eliminate any of your perspective error. So really, what you should probably think about is how could you design the experiment to get better data and avoid perspective error altogether. Number one, you can do a whole bunch of math if you wanted to and figure out how to counteract this perspective error, which is one possible method. But could you redesign the experiment to avoid this altogether?